Excellent. So today I'm going to tell you about BlindBox, which addresses a very similar problem to MCTLS with a couple of changes. So BlindBox enables deep packet inspection directly over encrypted traffic. And what we focus on directly are middleboxes that inspect packet payloads by reconstructing the TCP byte streams. So they perform deep packet inspection, or DPI. And these devices include things like intrusion prevention systems, parental filtering devices, or exfiltration detection systems. Today we're mostly going to focus on intrusion prevention systems, although the techniques that we develop are applicable to the others as well. So let's walk through an example of what we're talking about here. Here we have Alice and Bob, and they're communicating over a network. And Bob wants some extra security over his connection. And so his service provider deploys an intrusion prevention system. And this intrusion prevention system is going to determine which connections are good and which connections are potentially malicious and should be blocked. The intrusion prevention system knows the difference between these two because it has a set of rules that it's learned from a rule generator. This is a company like McAfee or an organization like Emerging Threats. These folks have teams of analysts who go out and analyze the latest malware, JavaScript, SQL injection attacks, and they create a set of terms that are blacklisted. So these rules or signatures contain strings of data that, when observed in a TCP connection, are associated with an attack. And this is going to tell us whether or not the connection is malicious. So once the intrusion prevention system knows this, if Alice decides to be malicious and sends an attack message, it can see one of the terms that from its blacklist has been sent in the data, block the connection, and protect Bob. So a major challenge for DPI devices, like David already told you about, is the increasing use of encryption. And clients have a really good reason to deploy encryption. Not only are they worried about their neighbors maybe spoofing over them over Wi-Fi, but oftentimes they're even concerned about their ISPs. This may be the exact entity who's providing them the DPI service, selling their data to marketers. So if Bob wants privacy, he's going to opt into HTTPS. But now this means that Alice and Bob have a secret key that the Middlebox doesn't know about. And when Alice sends her message, the Middlebox won't know what to do with it. So Bob isn't going to get the benefits of intrusion prevention. And the state-of-the-art solution, this man-in-the-middling approach, doesn't give Bob the privacy that he wants. The Middlebox has the ability to read all of his traffic. So what Bob wants here is a combination of both privacy and functionality. And it might seem at first that these two requirements together are conflicting. How can he have the privacy that the communication he has between his and his endpoint remains private to all other parties, while still allowing a third party to detect malicious behavior in the connection? It's almost like we're asking, can he have his cake and eat it too? But the answer is actually yes. We know it's yes because we built BlindBox. BlindBox is the first system that allows DPI middleboxes to inspect traffic without having to decrypt the traffic. It can detect blacklisted keywords in encrypted connections, but it learns virtually nothing about connections that do not contain blacklisted terms. BlindBox comes with a strong privacy guarantee that's backed up by a proof of security in our technical report. It's on the Cryptology ePrint archive if you're interested in checking it out. BlindBox also achieves practical network performance, so the forwarding rate at the Middlebox is comparable to what DPI devices get today for standard IDS deployments. And finally, BlindBox also supports a wide range of functionality. Not only does it support exact match detection, but it also supports regular expressions and scripted analysis. So let's look at the setup. BlindBox leaves most of the setup exactly the same as how you use intrusion detection today. We have Alice, Bob, their Middlebox, and our rule generator, this third party. The threat model also remains remarkably similar to what we use in IDSs today. And there are a couple of properties, a couple of assumptions baked into how we use these systems. reasons. I don't think they can hear me. Can you hear me?
Yeah.
You can hear me? We're good. Okay. This is for 2 reasons. There's a security argument for it. First of all, if the users don't know the rules, it raises the bar for what a user needs to do in order to evade attack. But the second argument, which was really important with the vendors we talked to, was that the vendors don't want to release their rules publicly. In practice, they release them in binaries directly to software running at the Middleboxes because they could treat these rules as trade secrets. They're the secret sauce that makes their service better than the other rule generators. The third assumption based in the world today is the one that we're going to change. Today, when Alice and Bob use an IDS, they trust that the IDS is going to run detection functionality correctly. But they also implicitly have one other assumption, which is that the IDS can be trusted with their privacy. This is the assumption we're going to change. We're going to allow that the Middlebox is actually curious about what's going on. There's a network administrator who wants to sort of sneak in and snoop on what Alice and Bob are doing. Or maybe there's an ISP that's tempted to sell data to marketers. Alice and Bob are going to retain their privacy despite this threat. So to opt in to using BlindBox, Alice and Bob install a new protocol, BlindBox HTTPS. And so we're looking at Alice and Bob's protocol stacks here, and by default, we leave the normal HTTPS stack unchanged. We use SSL unmodified. When the message comes in, it's encrypted by your normal SSL or TLS connection, sent to Bob, who decrypts it and reads the data out. We're going to add some new components to this system. The first component we're adding is a handshake. So this handshake is a handshake between clients and the Middlebox. Both parties engage in this handshake. And what it gives the Middlebox is a set of encrypted rules. So it's the Middlebox's rule set in a new and encrypted form that's going to allow the Middlebox to perform detection over the communication between Alice and Bob. The second thing we're going to add is another encryption module. So when Alice encrypts her data, it goes over the normal encrypted channel as well as through this BlindBox encryption channel. Now this BlindBox encryption channel generates the encrypted stream that the Middlebox operates over. And it's going to generate a set of encrypted tokens that are encrypted in such a way that when the Middlebox compares it to the encrypted rules in its blacklist, it can detect whether or not a blacklisted term is present. The last thing that we add is a verification step. When Bob receives these encrypted tokens, he's going to verify that Alice performed the protocol honestly. And that's to make sure that she doesn't evade detection. Do you want me to stand? I see. Okay, thanks. And that's to make sure that she doesn't evade detection. So today we're mostly going to talk about the BlindBox encryption module and how detection works at the Middlebox. But before we do that, we briefly need to talk about how the BlindBox handshake works. Because the BlindBox handshake is actually based on known techniques, we're not going to talk about it for very long. In fact, I only have a 1-slide introduction to what it does. The BlindBox handshake is an exchange between the Middlebox and the client at the beginning of a new connection. At the beginning of the connection, the clients know a secret key K. The Middlebox does not know K, and it does not learn K. Also at the beginning of the connection, the Middlebox and the rule generator know their rules. But once again, the client does not know the rules, and it does not learn the rules. However, the output of the handshake process is that we generate an AES encryption of every keyword in the rule set, encrypted with the client's secret key. And importantly, this operation will only succeed if there is a signature from the rule set for that keyword. Now, this seems quite counterintuitive. How could I compute this joint function, the encryption of a keyword with the secret key, without either parties learning both pieces of data? But there's actually a known technique to implement this from the security and cryptography community called garbled circuits and oblivious transfer. So that's how we achieve it, and that's the last I'm going to say about it. The key thing to take away is that the Middlebox is going to be able to learn these encrypted keywords. Now that we know that the Middlebox has learned these encrypted keywords, we can talk about what it does with them. The blacklist has now been updated with all of these encrypted values. They're encrypted with the client's keys. And now Alice and Bob are going to send their data over their encrypted BlindBox channel. So when Alice has a long message to send, say it has the phrase example attack, what she's going to do is she's going to tokenize this message along a sliding window. In our examples today, the sliding window is going to be 6 characters long. In practice, it's longer. So in the sliding window, she's going to take the first 6 characters, example, and she's going to encrypt them with her key. And she's going to do this iteratively along the window. Eventually, she's going to get to the term attack, which exactly matches one of the values in the blacklist. So if we did this, Alice would be able to send her traffic, and the Middlebox wouldn't know what's in any of those tokens unless one of the tokens contains a value in the blacklist. So we're doing pretty good there, right? Well, there's actually a slight problem with that design, although it gives us the intuition for how this is going to work. And that problem is as follows. Let's say Alice is innocent here. She's got a little halo. And Alice wants to send the completely innocent message, "I love muffins. What's your favorite muffin?" Now, the term muffin appears twice in this message. And so Alice is going to encrypt the term muffin twice. And that's going to result in the same output because they're both the AES encryption with her secret key of the same term. And the Middlebox can notice this. Now, this seems like a small bit of information, but it actually violates our goal quite strongly because these terms are not malicious, and the Middlebox is now able to perform a frequency analysis attack over Alice and Bob's communication. And surprisingly, frequency analysis attacks can actually leak quite a bit of data about what Alice and Bob are up to. So to solve this problem, we can go back to the literature of searchable encryption approaches. You guys have already learned about one searchable encryption approach. It's called deterministic searchable encryption, and it's the strawman that we just saw. But the security property that deterministic searchable encryption gives you is weak. It's weak because it's prone to these frequency analysis attacks. Instead, we might use randomized searchable encryption, which was a technique proposed by Song et al. Back in 2000. It has a stronger security guarantee because it's not prone to these frequency analysis attacks, but it has a different problem. The detection speed with randomized searchable encryption is much slower than deterministic searchable encryption. Let's understand why that is. At the Middlebox today, oh, my animations are disappearing. There we go. At the Middlebox today, when I have my plain text terms, the Middlebox at startup compiles these plain text terms into a data structure that allows it to quickly search through all of the rules at once when plain text data comes in. And using the deterministic encryption scheme, we can construct a search tree out of all of our encrypted rules. So when a new token comes in, it takes log number of rules steps in order to decide whether or not we have a match for that token. But randomized searchable encryption requires that we run a function over every rule whenever we want to match a token. So this takes a long time. With BlindBox, we want to have the speed of deterministic encryption, that is a fast and logarithmic lookup through the rules to decide whether or not a token matches a rule set. But we want the security of randomization so that we don't have these frequency analysis attacks. So let's see how we can make that happen. Once again, we have Alice here. Alice has the same message. She has her set of tokens. And what we want to design is an encryption scheme such that Alice's encryption will never generate the same token twice. Here's how she does that. At session start, Alice is going to pre-compute an initial salt value. This is a random number that she pulls out of the air. This salt value, salt sub 0, she's going to use to encrypt her values as follows. First, for every token she wants to send, every substring from her sliding window, she's going to encrypt it using her secret key, just like we did before for the deterministic scheme. But then we're going to do another encryption operation. We're going to take that secret key, or we're going to take that encrypted value, and we're going to treat it as a new secret key. And we're going to use that encrypted value to re-encrypt the salt value. Now, what Alice is going to do when she encrypts her token looks something like this. I have the AES encryption of my salt encrypted by the AES encryption of my substring. And I'm going to do this in my sliding window, just like normal, using the same salt for all tokens. However, when I run into the word muffin again, I'm going to use a new salt. We'll call this salt sub 1, and we generate it by applying a deterministic function to salt sub 0. So now that we've encrypted it twice with two different salts, even though the term muffin has showed up twice, we had two different tokens come out. So Alice's data is no longer subject to frequency analysis attacks. However, by changing the encryption scheme, we now need to change how we do lookups at the Middlebox. So here's what the Middlebox does. After the BlindBox handshake, the client sends the Middlebox salt sub 0. Because the Middlebox already has the encrypted rules, encrypted with Alice's key, it can generate encrypted tokens, just like Alice did. This is going to output an encrypted value, and now the Middlebox can pre-compute a search tree with all of these terms one by one. Alongside the data that is encrypted, we're going to store the keyword and the salt next to it. Now that we have this search tree, the Middlebox can detect matches and order log number of rules because we've sorted the search tree according to the encrypted value. So when a token comes in, we find the node in the tree that matches in log number of steps. And then if we have a match, we can follow our normal order of operations. So on match, we need to respond. There are one of two things that can happen. On average, a rule requires 3 matches in order to detect an attack. A given signature that represents an attack contains 3 different keywords. If this is the final keyword that we need to detect an attack, we can sever the connection and we're done. But if it's not the final keyword, we need to do some updates to the tree. And the reason we need to update the tree is because this term might show up again. And so if Alice re-encrypts it with a new salt, we need to be able to find it that second time. So to update, we pull out this data that we stored in the tree, recompute the value using the added salt, which is computed using a deterministic function from the salt that we already know, and then we put it back in the tree. So now using this scheme, we can say that BlindBox has both the security of the randomized searchable encryption, no frequency analysis attacks, and a fast detection speed that runs an order log number of rules. Now let's recap what we've seen. BlindBox uses a new HTTPS suite that the clients opt into. It adds some additional modules to SSL or TLS, but it does not modify those base encryption schemes. At the start of a session, we use a BlindBox handshake that allows the Middlebox to learn some encrypted rules. And the BlindBox encryption step generates randomized tokens, but the Middlebox can still do fast exact match lookups over these tokens. Now, there's a lot of other information in the paper about how BlindBox works, how we optimize, and also how we support regular expressions, which I don't have time to talk about today. Today, we talked about how to do exact match detections, but in the paper, we talk about how to handle regular expressions and scripts. For example, let's say that Alice sends the message with some attack coordinates. And normally, what my IDS would like to do is extract these attack coordinates and report them back to an administrator. We would need to run some sort of script over the plaintext data to do this. Now, unfortunately, doing regular expressions or scripted analysis over encrypted data at the same privacy level that we guaranteed with our exact match lookups is an open problem. No cryptographers know how to do it fast. And so what we do to support regular expressions is we offer a second protocol that supports a different privacy model called probable cause privacy. And it's slightly weaker. It allows the Middlebox to learn more about the data. But this weaker privacy model will allow us to do scripted analysis. So see our paper to check out how that works. You can also check out the paper to learn about our optimizations to reduce bandwidth overhead, how the handshake works, detailed evaluation and comparisons, and what the difference between these two privacy models are. So please do come see our paper or chat with me after the session. But before we go, let me give you some evaluation highlights. We evaluated BlindBox on 2 vectors. One is functionality. What kind of IDS behaviors can we support? And the other is performance. How fast is it? When it comes to evaluating functionality, we looked at a couple of different rule sets. We first looked at the base scheme we talked about today, this exact match model of lookups. And for document watermarking and parental filtering, we rely only on exact match detection for correctness. So we can support 100% of the things that these systems do. But for more general intrusion detection systems like the Snort datasets or 2 commercial datasets we got from StoneSoft and Lastline, we would only be able to support between 29 and 67% of the rules that they apply across traffic. And that's because many of their rules rely on regular expressions and scripts to complete analysis. So for those, in order to get 100% coverage, we would have to move to our weaker privacy model. When it comes to performance, we looked at a couple of different factors. I'm going to give you a couple of highlights here. For forwarding weight at the Middlebox, we achieved our goal. BlindBox can forward at 186 megabits per second, which is comparable to Snort in existing IDS deployments. So that was a success in that we can do these fast exact match lookups. But the BlindBox handshake is still very expensive. For the last line rule set, it would take 97 seconds to complete that exchange. For smaller rule sets, we can do it in a couple of milliseconds. But this setup time means that IDS-like inspection is only reasonable for long-lived and persistent connections with BlindBox as it stands today. Page load times also increase, somewhere between 15 and 100%. This is within normal variation depending on connection quality. So what these comparisons are showing us is the difference between unencrypted traffic and BlindBox when it comes to the forwarding rate, and BlindBox and SSL when it comes to the setup time and page load times. These aren't quite fair comparisons because those techniques don't actually allow us to do analysis. When we compare against existing encryption schemes, we can say that BlindBox is 3 orders of magnitude faster than searchable encryption, and it's 10 orders of magnitude faster than functional encryption. So this is a major step towards being able to achieve our goal. But it's only the first of many steps towards our eventual end goal, which I'm going to tell you about on the next slide. BlindBox is the first system that allows DPI Middleboxes to inspect traffic without decrypting the traffic. But in future work, we're working on generating a new protocol, one that will allow us to generalize BlindBox to a protocol that will support all Middleboxes without having to sacrifice privacy. Thanks very much.
Hi, Brian Trammell, ETH. Thank you for the interesting crypto work. I'm a little bit. I'm not used to connection setup latencies measured in the millions of microseconds.
I know it's the worst.
So 97 million microseconds. I've run off the. So I'm a little bit surprised by sort of the second to last slide. So you basically talk about doing basic regular expression matching in a sort of reduced privacy environment or token matching. Yeah, so this slide here. I kind of stopped paying attention to IDSs a while ago because I don't think that they work. But I really don't think that IDSs that are looking just simply at substrings work at all. Because most of what so there's document watermarking and there's exfiltration protection. And in some cases, the data formats that you're looking at are going to be deterministic enough that you can actually do substring matches. But what we really care about is malware. And malware has been polymorphic for a decade or more, maybe. So in terms of actually looking at the types of attacks that are causing actual problems, can you talk about how you would apply something like this to a environment in which malware is polymorphic? So it basically encrypts itself in order to get around the signature-based IDS.
I actually don't agree with that conjecture. People use matching IDSs all the time, and they wouldn't use them.
Oh, they use them all the time. The conjecture is that they don't work. That it's basically you're generating a 99+% false positive rate, and I mean it's a lot of. Okay, I'm not going to have the argument with the. I'm not going to have the argument with the market. The market has decided that it wants these, so. Actually, let me read the paper about the weaker privacy model because I'm not really convinced that this in an environment where you're just doing substring matches is of much use. But let me take a look at the paper on the other. Thank you.
Hello, Marcel Waldvogel. Thank you very much for your nice talk, and I enjoyed it very much. When you talk about the frequency analysis, just placing that marker at a different point in the search tree does not prevent frequency analysis because you still know that it was the original marker. Or am I not understanding it correctly?
So once I've detected that there's a match, we want the Middlebox to learn that data. So if there is a match, of course you should be able to do frequency analysis over substrings that match. The point is that innocent data that doesn't match an attack signature should not reveal anything.
Okay, thanks.
Thank you, very nice talk. I have one simple question. If Alice would be an attacker, why would Alice actually talk to your BlindBox at all?
That's a great question. Bob needs to decide what his security level is, and increasingly people use, let me back up on that question. if BlindBox HTTPS were to become the standard and users weren't going to connect to random servers without using BlindBox HTTPS, Alice would have to in order to be able to communicate with Bob. It would be expected for her to be able to actually execute her attack.
So basically,
so if my bank, Facebook, Google have all adopted BlindBox HTTPS, and Bob doesn't see the little like icon on the screen, he's not going to connect to Alice's website.
But Alice is the one who opens the connection, right? So Alice decides to use BlindBox or not.
Right, both Alice. So today, when I connect to my bank's website, I see a little green lock icon.
Yeah.
If I go to a fake website, they're going to try and spoof that little green lock icon. And if they can't, then that's a signal to me that something wrong has happened. And so the idea would be that in a model of the world in which everyone has adopted BlindBox HTTPS, that little green lock icon isn't going to show up for Bob. And he's going to know that something's up if Alice isn't using it. So Alice is either going to opt into BlindBox and try somehow to evade it, or Alice isn't, and Bob's going to get a signal that something fishy is going on.
So you don't want to deprecate HTTPS, right? Which we are currently using. You say that's evil.
I didn't follow that question.
So you want to say if you only use HTTPS, what we're doing right now, that's evil. That would be the step you have to do.
That's evil.
That's evil. That's not valid anymore.
Yeah, maybe we should take.
Yes, that would be the idea. That if I have a trusted network service that I'm expected to be using.
I'm not sure we can do this from today to tomorrow. Yeah.
Hi, I have a question about the performance numbers.
Yep.
So you said something about 190 some megabits per second. That's like almost 3 orders of magnitude slower than the commercial IDS boxes I'm familiar with that are
For a single core? That's one core.
Oh, okay.
So they usually achieve higher throughputs by parallelism, and so we could also parallelize.
Okay, so I guess following up on that, what's the bottleneck in the performance that you're seeing? I mean, you're gaining throughput by just adding more cores, but what's slowing down
the biggest cost for BlindBox is really the handshake. That's what's killing us, and that's what we need to go back and revisit. In terms of the bottleneck is in terms of throughput, it's just the number of tokens that you have to match over. And so we spend a lot of time, and we talk about this a lot in the paper, reducing the number of tokens that you have to match. Because the fewer tokens that you have to look through, then the less analysis you have to do with the Middlebox.
What do you do about behavioral IDS? I mean, it's a little bit of a follow-up to the other question, but signature-based IDS is pretty limited. Most of these boxes do behavioral IDS as well.
So in the paper, we talk about this probable cause privacy model, where so if I have a regular expression, for example, in my IDS, usually what an IDS does today is it detects a couple of exact matches, because exact matches are fast to detect. And then only if the exact matches have shown up does it go on and do the scripted or regular expression-based analysis. And so starting from that point, we designed an encryption scheme that has that baked in. You do the exact match detection model, and then in the new encryption protocol that supports scripts and regular expressions, once you have an exact match, that's actually sufficient to reveal the session key. And then I can decrypt it and do whatever analysis I want. But this gives a stronger guarantee than what you would have decrypting all sessions, because only once there's enough of these exact match detections to determine that the connection is already suspicious do you have the ability to do the scripts.
Okay, thanks.
Okay, quick question. So, given that the endpoints don't learn any of the keywords that Middleboxes are using,
yep.
What's to prevent the Middlebox from introducing a wide range of additional keywords to do frequency analysis or inspect your data in some other way?
Right, so that BlindBox handshake operation only succeeds if the keywords are signed by a trusted rule generator. So I would install sort of in my certificate library that I trust McAfee, Symantec, Emerging Threats, these guys. And if I have a signature from them, I know the rules are good. And if I don't, this handshake doesn't succeed.
Hi, so I really enjoyed your talk. So one quick question. So you showed the 97-second setup time.
Right.
Is there any hope to getting it down? And if so, how would you, that seems prohibitively high.
It's really, there are a lot of systems, especially in the security community, that rely on this technique, and they're working on making it faster. I am sort of a systems cryptographer. I take the tools and I use them. And generating the sort of blind box encryption stuff was a little bit of cryptography, but mostly it was still using existing tools. I really hope that somebody smarter than me figures out how to solve this multi-party computation problem faster. But there are a bunch of different, they call the general class of things that this handshake is in is called a multi-party computation problem. And there are a lot of really smart cryptographers who work on it. And so I leave it to them.
Cool. I had one other question, which is a related question to Nick's comment. So I thought his question was about behavioral IDSs, which is sort of looking at connection patterns and IDSs that look for signatures in pattern connection, how requests are sent and things of that kind. It was not clear to me how your system would work for such behavioral IDSs. It seems like it's more applicable to IDSs that do regular expression matching over the payload of network data. So can you comment on how it would apply?
So much of that behavioral analysis is really about connection frequency, who I'm talking to, and all of that stuff remains unencrypted. It is true that there is some behavioral analysis that goes on in what's in the payload, but a lot of that behavioral stuff is actually sort of unencrypted metadata about what I've seen the party do in the past. And all of that is left in the clear.
Okay, thanks.
James Sung from Facebook.
Yep.
The first response, the first impression of this work to me is that this is a perfect tool for the graphite voice of China. But there's one problem, because Chinese people use Chinese. So it seems like your approach is more English-centric, in terms that you need to tokenize your text very easily, and you encrypt each word of them. In Chinese language, there's no clear separation, like space between words. So is that how your approach will apply to those languages? Do you have any ideas?
All right, I want to respond to two things. I would not use this protocol or HTTPS in general were I in China. I would use a VPN. Second of all, we tokenize along actually the byte boundaries. It's not necessarily character based. So we also tokenize some sort of binary data as well in exactly the same way.
Okay.
One last question.
Last quick question. Hi, Jitu Bhatia from MSR. The key thing here is that you said that IDS systems that deal with unencrypted traffic on the client is not something that you are concerned with here, because you believe that IDS operators want to keep their rule sets secret. Can you talk a little bit more about that?
Sorry, can you say that again?
I mean, you wouldn't have to run a Middlebox like this if you could simply check the traffic after it's been decrypted on the client, right? Correct. If you could check the traffic on Bob, you're all set. The reason you don't want to do that is you believe that IDS operators don't want to publish their rule sets. So is that true? I mean, you have a number of virus scanners and signatures that are now routinely pushed to the clients. You gave McAfee as an example. McAfee's and Windows Defender, we ship virus scanning rules.
There are a couple of other reasons that people use IDSs rather than running, or they tend to run both. But when you have it out in the network, it's a different trust base. So even if my laptop is compromised, the network is going to check it. One of the things that was the motivation for this work was that a friend of mine went and visited another university, and they had a really strong IDS policy. And in order to use their network, you had to install a certificate that allowed them to read all of your traffic. And so that was something that he was kind of okay with IDS running there, but he didn't really know these people, and he didn't really want to give them that ability necessarily. So there are a lot of different reasons that people use Middleboxes, and this is an argument that SIGCOMM has had for a couple of decades now about what functionality belongs in the network or what functionality belongs at the edge. But the bottom line is that people are doing it in the network, and BlindBox exists to support that use case because people want it.
I agree with that. That's fine. But I mean, even on the client, people have now trusted computing base and other technologies where the rule set doesn't necessarily have to be revealed to the client. You can impose a number of other things. Intel is coming out with processor extensions that let you do these things.
That is an alternative approach people have looked into.
Okay, thanks.
All right. So let's thank Justine.